occurs.
Thank you, Daniele. Thanks for having us here. So I will actually cover a line of work on this direction, and this is some joint collaboration with some of the people that I listed here, besides the two of us, Gilbert Baumslag, Kevin Iga, Ludovic Perret, Vladimir Spirlane, and William Skip III. So since it's Friday afternoon and is our last talk of the great workshop, I guess everybody is by now tired of the great technical talk, and let me take a minute to thank the organizer for this great event. So I just want to give a brief highlight of the topic that I will cover in this talk, so that if you have to leave, at least you know what is going to happen during the rest of the slides. The goal that we seek to achieve is to find alternative intractability assumption from combinatorial group theory, such that, well, first of all, we would like to use them for some cryptographic application, and second, we would like to have some evidence, to establish some evidence about the hardness of this assumption, and in particular, in our specific case, we will introduce a new intractability assumption, and we will prove some random self-reducibility property about this new assumption. And our approach that we decided to follow, it was a bit different than what has been done with the previous group theoretic approach, in the sense that we want to start with some that we all know and love, which is learning with errors, and we are going to try to generalize this notion, and then in particular we are going to instantiate this generalization to a specific class of groups, non-commutative groups. And so what are the groups? So this was a long discussion with one of my collaborators, Gilbert Baumslag, that he was a great group theoretician, which unfortunately died recently. And we all had this amazing discussion. And one day he said, okay, what about looking at these Burnside groups? So we were discussing all the property that we wanted from a cryptographic point of view, and say, okay, what about Burnside groups? And me, I say, okay, what about them? So I guess since, from my perspective, we all are not very familiar with these Burnside groups, what I'm going to do is start with a background on these Burnside groups, and then follow with the description of the generalization of the LWE assumption that we call learning Burnside homomorphism with noise. And then Antonio will discuss the hardness, the random self-reducibility of this new assumption, and if time permits, he will also describe some of the application of this assumption. Okay, so let's start with Burnside groups. Well, these in the group theory community, they have been studied extensively. They are not new groups, so for them, they have been looking at them for a long time, but from a different perspective. So what they are looking at is if I give you a group and the order of the elements in this group, if it's finite, so all the elements in this group are finite order, what about the finiteness of the group? Is necessarily the group finite or not? So this is one of the questions that they look in this setting. Or alternatively, what the combinatorial structure of these groups? So let's see an informal definition of the Burnside groups. So I'm going to denote with this symbol B and M for the most generic group with n generators, where the order of all the elements divide M. And so the generator, I'm going to use the notation just x1, x2, xn. So if you like, you can think of them like the indeterminates in a multivariate polynomial. And the elements in this group is just a sequence of generators and the inverse, one after the other. And the identity in this group is the empty sequence. And the most important condition is the following. For every element in the group, B and M, the element to the exponent M is equal to the identity in the group. And since we are using the multiplicative notation, then I'm using just Wm equal to 1. Okay, so as I say, this group have been studied a lot, and analyzing the characteristic of this group is not so easy. So not a lot is known for these Burnside groups. So in the specific case, for example, of m, the exponent, equal to 2, this is known. This group is finite. And it's in particular is abelian, and you can think this is isomorphic to the n vector space over F2. So this is actually something that we can think of this as a familiar object. But what about m equal 3? Well, m equal 3 is also well studied, and we know a lot about it. It's finite, so this is already a good thing that one of the properties that we discussed we wanted is finite. Good. It's non-commutative, so at least we move away from the abelian case, otherwise it's kind of not our point. And it's not isomorphic to F3n, so that's no. This is in fact much larger. And then when we move for higher value of m, things get very complicated. Well, 4 is kind of easy. We know it's finite because you can see this as a combination of the other two smaller groups, and same thing for 6. But then if you start by considering m equal 5 or 7, people don't know. Is it finite, infinite? I don't know. So then we move to the other side of the spectrum for m large, and here m large, really what I mean is on the order of 100, something like that, just for have a specific number in mind. Then the Burnside group become infinite.
So the question is if this group is finite for every n. So you fix
you fix the exponent, and that, yeah. So even though, so I give you a group, and the order of the group is, so the order of all the elements is finite, is it this group infinite or finite? So
you have a finite, you have an infinite family of groups depending on how many generators you have, and then for each one you have a finite group, and then of course they are all finite, but they get bigger and bigger.
In particular for m large, then you in this case of Burnside group B and m, for m large is infinite.
Even for a specific value of n, maybe n equal to, I don't know,
10. 10, yeah. So okay, so we looked at this Burnside group and say, okay, where do we start? Well, we start from the first one that is not the familiar one. So it's finite, which is our first, one of our main prerequisites, and is not commutative. So let's start from this one. So for the rest of the talk, I'm going to focus to m equals 3, and for brevity, I'll just denote as Bn. Okay, so if I write again the definition, essentially the only things that we have changed is, again, the generator are x1, x2, xn, the element are sequence of the generator and the inverse, and the exponent condition just says W3 equal 1, but now W3, what does it mean? The concatenation of W 3 times, so W is equal to 1. And so I put most generic in quotes. So what do I mean by most generic? By most generic, it means that the only non-trivial identity in Bn are the one that follow from the exponent condition. And that's it. So two important consequences of this is that Bn is not commutative, because if you want to look at this element x1, xj, well, the only way I can get a 1 is by length 3 of something of length 3, so I only have two generators, so it's not going to be commutative. So xi, xj is not equal to xj, xi for every I different than j. And the group operation is defined formally as so if I have two elements, W1 and W2, multiply two elements just means, put W1 and then following W2. So just the concatenation. But when you put two words one next to the other, at the border of the end of W1 at the beginning of W2, you may have some simplification. So what you get is the product of these two words, W1 and W2. So Bn is, as I said in the previous slide, is not commutative, but we are kind of used to this commutative property. So is there some hope that maybe I can reach some sort of commutativity? And so one thing that I notice is that if I define what is called the two-commutator, which is this symbol of the pair of these xi, xj, then I can get something close to the commutativity. And in particular, I get that xi, xj is equal to xj, xi concatenated this extra value that is called the two-commutator. So I say that, I get the commutativity with some extra payoff. So I get the equality, but with an extra term. And then you can also similarly define the three-commutator, which is the commutator with three elements, which, not surprisingly, is the commutator of the first two elements, and then the commutator with the third element, in this case. Okay, well, you can, in general, extend this definition of commutator to L element, but for the specific group that we are focusing, Bn, remember where M is fixed to be 3, then in this case we have this important equality, which the commutator of weight 4, so the commutator with 4 elements is equal to 1. So essentially the sequence stops there at weight 4. So of course you can stop me at any time. Antonio will be happy to answer all the questions. Okay. So what are the important property that follow from this equality? That xi, xj, xk, xh is equal to 1. First of all, that the commutator of weight 3, so the 3 commutator, commutes with everything. So this is really good. So it means that if I have a word and somehow I want to swap the 3 commutator with another element, I don't have to pay any payload. I can just swap it and nothing will happen. So this is something that we like. Yes?
Is it easy to explain why the 4 commutator is?
So it's not difficult, but it requires a proof. I can do it offline. But, it's a line, but it's not, it requires a proof.
This is what you had before in the previous slide?
Yeah. Sorry. So you have to prove, but you can prove that if you consider the commutator of weight 4, so x1, x2, x3, x4, this is equal to 1. And again, with a proof, you can, which I'm omitting for the sake of time in the talk, but I can do it on the board if you want. This implies that if I consider a commutator of weight 3, these commute with everything, and it doesn't add any extra element in the sequence.
So what is the best way to think of these commutators? Just the definition that you have in the previous slide?
Sorry, I'm going forward. So for weight 2, this is the element such that if you add this on this equality, it will make xi xj equal to xj xi. Because the way we define the commutator of weight 2 is equal to xi inverse xj inverse xi xj. So if you plug this in here, essentially you have that xi inverse simplify this xi, xj inverse grid of this one, so you get the equality.
But then in the case of 3 commutator, what's the property of the 3 commutator?
The property is that so the commutator of, you can think of the 3 commutator as the commutator of the first 2. And then, so in that case, it will be xi inverse, xj inverse, xi xj, and then the result, you do the commutator of weight 2 with xk.
No, yeah, I see how to build it. The question
which in
is,
particular,
what does it, is something that if you multiply xi jk by the commutator, then you get a rotation? Or?
Yeah. So, and notice in particular that in Burnside groups, it would be equivalent to define the 3 commutator as xi commutator, the xj, xk, but in general it's not true. But for this Burnside group, it's true. Okay, so the first important property that we're going to need for the next points is that the commutator weight 3 swap with everything. And the other important property that, again, with the proof followed by the fact that the commutator weight 4 is equal to 1, is that two commutators commute among themselves. So I don't have to pay anything when I swap two commutators. And I do have other property that are useful for the proof, but let me skip it because we are not going to use it in the talk, but I just put it there for the recording, essentially. But what I want to point out in this point is that for simplicity, we are going to assume that within the commutator, the order of the generators is lexicographic. So they are ordered in lexicographic order. If you want to swap xi with xj within the commutator, then this will affect the exponent by a minus sign. Okay, so now really, if I have to deal with this element, I really have to look at the structure. So, but somehow I need some hope that in this specific group that I'm considering, the structure of all the elements is, is uniform. So in particular, in general, I cannot say that in non-commutative group, all the elements may present multiple representation. So in particular, this means that if I can represent an element in multiple ways, then it's going to be hard to compare, to do the equality testing with the element. So for example, in Burnside groups, so if I consider this element xi, xj inverse xi, this is equal to xj, xi inverse xj, which at the first look, they look quite different. In fact, you would think that they are not the same element, but you can prove. So essentially, maybe I'll do it on the board. So if you start with the xi, xj inverse, and then xi, I can multiply on the right by xj inverse, then xi inverse xi, and then by xj inverse, and that this will give me 1. And indeed, if I look at this element, I can see that this is the repetition of the same element 3 times. So essentially, this it's indeed correct because it's the exponent condition that W3 is equal to 1. So the nice thing about this group is that all the elements can be represented in a very compact normal form. So all the elements will have this structure, so can be seen as a sequence of the product of the generator with some exponent. But remember, the exponent could be 0, 1, or 2, or for simplicity, I'm using the -1 notation, followed by the product of the commutator of weight 2, so the two commutator, again, with an exponent that could be -1, 0, 1, followed by the product of the 3 commutators. So this is really nice. So what I'm saying is whatever element you give to me, first I can convert this in this normal form, which is very nice. It has a very specific, well-defined structure. So once everything is in this normal form, I can start to do the comparison, even just looking at the exponent. So again, so now, of course, of this, I have exactly n if I also put the exponent 0, order of n, if you don't want to write that element. And then this will be of the order of n squared because it's n choose 2. And this is of the order of n cubed because it's n choose 3. So overall, the representation, okay, let me go back. The representation of an element has length n cube. The order of n cube, yes.
So it's because you can use the two commutators to sort the x's.
Yes.
And Then you can push the two commutators to the right using the three commutators, and the three commutators, they commute with everything, so you can...
Perfect. So it is what you just said, but I want to prove that indeed it is an efficient algorithm. It's called the collecting process, and I'm going to talk about it in just a couple of slides. The only thing I have to prove to you that is efficient, is not exponential, and that's what I'm going to prove it next. But before we go to that point, let me do an example. So let's fix n equals 2. And let's consider B2, so M is equal 3 and N is equal 2, so just two generators, X1 and X2. And was this a great picture here, at least I think it's great. So essentially look at the square to represent the elements, and the edge represent the multiplication. So if I start from one element here, and I wanna multiply by x2, then I'm gonna follow a purple edge, and if I wanna multiply by x2 inverse, then I follow the edge in the reverse direction. And same thing for if I want to multiply by x1. So this means that I'm multiplying this element by x1. And notice already that if I multiply 3 times by x1, it means that I go x1, 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 so I get the identity. Okay? So this is called the Cayley graph of B2. And B2 has 27 elements, and they are all written in this normal form, that in this case it just means the first generator x1 to the exponent minus 1, 0, 1, depending on the element, and then x2 to another exponent minus 1, 0, 1, followed by the commutator, but in this case, two commutator, which in this case is only x1, x2 to the exponent minus 1, 0, 1. Okay, so since Craig is in the audience, he said, okay, I like that, but what about putting everything in a matrix form so that I can think of them as multiplying instead of concatenation? And for the case of B2, this group B2 is isomorphic to the Heisenberg group, so where all the elements can be represented as the following matrix, triangular matrix, and on the upper part, you have the exponent of the first generator, the second generator, and the two commutators. So in this case, I can think of the multiplication as the products of the two matrices that result from writing the two elements in this matrix form. So for B2 is actually nice. I have a nice way of mapping to what is familiar to us. However, if we try to go, B3, then things don't map again back to this group. So there are no known polynomial order representation of Bn. So really, if you have to like this group, you have to to work on this concatenation and on the collecting process that I'm going to describe in order to multiply the element. So really we have to discuss the group operation. So remember the normal form. And pictorially, I'd like to, for the next slides, to think of this as the red part is the sequence of the generators, the green part is the sequence of the two commutators, and the blue part is the sequence of the three commutators. As we discussed before, this is in the order of n, this is order n square, and this is order of n cube. Okay? So to multiply two elements, we just put one after the other, but now it's not in normal form. So essentially, I would like to move the blue toward the blue, the green all together, and the red all together. So this is called the collecting process, and I'm going to show that it takes time order of n cube, which is cubic in n, but is linear in the representation of the element. Okay, so first step is that I know that my friends are the commutator of weight 3 because they commute with everything. So the first thing I'm going to do is to move all of these toward the end of W2 and then add the corresponding exponent. Second, okay, so this I have to do for all the element in here, and each one I move in constant time. So these require n cube time. Good. Stage 2. Well, stage 2, I want to take care of the green part, the two commutators. So I want to move the two commutator sequence of the first word, W1, toward the two commutator in the group in the word 2. Okay, so let's look at the last two commutator in the sequence. When I swap this with the first generator of the second word, this is going to give rise to a 3 commutator. So I can swap them, but then it generates a 3 commutator, which is my friend. I can move it for free toward the end and sum the exponent. So for each one, two commutator that I consider in this sequence, I have to create these for all the generator in here. So for each one of them, I have to do n square running time. And then, since I have, order of n, I said the other way around. So for each one of them, I do order of n running time. Since I have order of n square, I get gain order of n cube. Right? Did I say at the end correct? I think I fixed it. Yeah. So also, so is this clear? So also second step takes time order of n cube. So the last step is the tricky part. So the last step is the one that I have to order in lexical graphic order all the generators. So I have all the group of generator of word 1 and the group of generator of the word 2, but I have to order them in lexicographic order. But remember, every time I swap x1 with x2, I create a 2 commutator. So if I consider xn here and x1 here, when I swap, I create the 2 commutator x1, xn, but now I have to move these all toward the green part, but for each one of them, I have to create a 3 commutator that goes toward the end. So for fixing each out of order generator takes order of n swaps. But as I said before I can go to the next generator, I have to fix this commutator of weight 2, which, as I said in the previous slide, takes order of n square time. Since I have order of n generators, overall I takes order of n times n square, so order of n cube steps, also for this third stage. So overall, the 3 stages, they all take order of n cube time, and so overall the algorithm to multiply two elements in the group is in the order of n cube.
The n cubed here is okay?
Yeah, because in this case is the length of the representation of the element in the group. So in this case is fine for this, yeah. So just to recap, so this is the normal form. The length, so the number of elements in Bn, if you count, is going to be 3 to n choose 2 plus n choose 3, so it's finite, but it has a lot of elements on the order of 3 to the n cube. And then the group operation is efficient. In particular, it's cubic in the security parameter, but is linear in the input size. And I didn't talk about the inversion, but it's somehow similar of concatenate, because you have to swap all W3, then the group 2 commutator, and then the generator, and then you have to move everything together. But essentially, it's a simpler description of the algorithm that I just described. So he also takes same running time, and it's not commutative, but enjoys several properties that are bringing us to something that we are familiar with. In particular, we have 2 important properties. W3 is equal 1, and x1, x2, x3, x4 is equal to 1. So now what it remains to say, okay, now we have this nice group. What can we say about the hardness of assumption?
I understand how you keep the normal form, but why is it important that we keep the normal form?
Because if I can translate all the elements in the same form, then I can compare them. In general, in groups, you can have, yes, you can have multiple ways of expressing the same, and then it will be hard to compare them. In this case, you can always convert to a normal form, but in this case, the normal form is also nice and compact, so the operation, the group operation, is also efficient.
These are all, you didn't show, but these are all different, these elements. Those written in normal form?
Yeah, yes.
It's not obvious.
No, you require proofs. So I'm going to leave the hard part to Antonio.
Okay, so I'm going to switch slightly here. We've done a wheel of properties of Burnside groups, and we'll try to see, okay, so now we think we can use them as a platform for computational operations. We know how to represent them in a compact way. We know how to operate with them. So we can do things with them efficiently. The question is, what's hard to do with them? And that's where the pitfalls usually arise in the context of group-theoretic cryptography, because you go into problems like the word problem, meaning try to recognize whether two elements are the same, and usually those problems are not they don't lend themselves to average case analysis. There are IMPR problems for general groups, not for this one, and it seems complicated to actually develop hard problems that way. So we took a different approach, and just so that we can maybe catch our breath with something that we are familiar with, the approach we took was to look back at learning with errors and see whether we could learn something from that, from that approach to things. So let me review learning with errors, although we've seen it several ways during the workshop. And differently from what we've done so far, we're going to take an algebraic look at learning with errors. There's a lot you can learn from learning with errors by looking at it geometrically. That's looking at the logic structure behind them. That's not what we're doing. We're looking at it algebraically. And there is something also we can extrapolate from that. So the setting of learning with errors, just to fix notation, I'm going to assume that the secret is called S, and that's a vector of length n. And there's going to be some perturbation using Gaussian noise, which is going to be the psi of n. And then we're going to consider these distributions over pairs, which are an element from fqn, a vector, and a scalar fq, obtained by setting a random vector and then a noisy inner product. So we're going to take an inner product with a secret S, and we're going to perturb it with Gaussian noise. So one way to look at it, besides inner products, is to think of these as a functional, linear functional. So you can think the inner product as a function from fqn to fq, and that's all linear functionals from the vector space fqn to the base field fq can be written as product by some vector. So really what's going on here, one way to look algebraically at LWE, is that you have a secret functional from the vector space fqn to the base field fq, and you give out preimages together with noisy images. You give out pairs A, B, where A is a random preimage and B is a noisy image of the secret functional. And then the assumption is that if you get access to distribution of preimages, noisy images, which is this A distribution, parameterized by the noise distribution and with the secret S, then that's distinguishable from the uniform distribution. That's the decisional version of the assumption. Of course, it's also equivalent to the search version. In our case, the equivalent is not clear, so I'm going to stick with the decisional version. And I'm not specifying whether S is random, whether S is arbitrary, because there is a worst case to average case reduction in that case, so it doesn't matter. So we can think of that as the LWE assumption. So once you look at LWE like this, we can say, okay, so if what's going on is that we have a secret functional linear function from the vector space to the base field, really we could even just look at them as groups that have an automorphism between them. Sure, this is a vector space over this field, but it's it's a group with in this case there is with respect to addition, and it's also a group with respect to addition. They have other structure, but they don't arise in this situation. They do arise in the applications of LWE to cryptography, but not for the assumption. And then you can think of it, what if I have two separate groups, G and P, which are not vector space necessarily, they are just bare bones groups, but they're compatible in the sense that I can have homomorphisms between G and P, and then the homomorphism between G and P is going to be your secret key, that's going to be the secret, and the distribution is going to give you random preimages in this first group G, together with a noisy homomorphism, with a noisy image. Phi of A times some noise distribution E, which you have to define. So for now I'm going to leave that indicated just as a psi distribution, which is not in the slide. And we call this a problem, this generalized version of LWE, we call that learning homomorphism in noise. Because the goal there is to learn what homomorphism is. Of course, I'm actually going to look at the digital version, so it's more like distinguish preimage pairs, but we're going to give the name of learning homomorphism in noise. So to compare and contrast the two assumptions, just one second. In the case of LWE, the secret is a functional, is a linear functional defined by the vector S, and the noise is defined by the Gaussian distribution. It's a small noise in FQ. Instead, we can always think of it as the secret is a homomorphism from a group G to another group P, and the noise must be small in some sense, and it's live in the group P. Yes?
Just a very basic question. So when you consider some analogs of standard linear algebra over a non-abelian group, is it even solvable without noise? We have systems?
No, exactly. It's a very good question. So the point here is that one of the reasons we look at LWE is because if you don't have noise, the problem is easy. And it's amazing that by adding a little bit of noise, the problem becomes hard, and it gives us a lot of power to do applications. In the case of non-commutative algebra, it's not clear that without noise, the problem is easy. And in fact, people have looked at that question, but we didn't feel like relying on that for computation for cryptographic hardness because it's difficult to make average case guarantees on that front. But it is, we don't know of any way of solving the problem without the noise either. It's just that the computational assumption becomes difficult to work with. So maybe that's one reason to like this in a non-commutative group, because it seems like it's going to be even harder than regular LWE, which you can. I'm sorry? It's going to be harder to apply. So that's indeed toward the end, I'm going to show that so far we only have mini-crypt application because of the non-commutativity. Okay, so to summarize what you need to define, this is an abstract framework, because you can define it for any pair of group G and P that are compatible. So you need two groups G and P. You need distribution over these groups, although most of the time they're going to be uniform distribution. Here I'm leaving open the hypothesis that maybe they're even infinite, and so the uniform distribution doesn't make sense for infinite. But what we'll see later on is going to be finite anyway. So we can think of gamma as a uniform distribution. Psi is going to be the error distribution, so that's going to take some work. And then maybe you also need the distribution over the secret keys, where the homomorphism from G to P. Although again, when it's uniform, when it's finite, you can go with the uniform distribution. And so the assumption is going to be, here's the same picture from before. You have a random A from the group, a random preimage, and a noisy image. And then the assumption is to distinguish those from random G and P. Of course, this makes sense for the finite case. For the infinite case, you can generalize without distributions, but we're not going to look into that here. And this distribution, I'm assuming it's, in this case, for a random homomorphism. In general, if you don't go into concrete settings, you cannot prove that this is equivalent to a worst case version where it doesn't matter and the homomorphism is arbitrary. So then let's first of all convince ourselves, very briefly, that this actually generalizes LWE, and of course it does because you just look at the additive group inside the vector space FPN with the uniform distribution. Then you look at the additive group inside the base field FP with a discrete Gaussian as a distribution for the noise. And then, of course, your homomorphism just always boils down to linear functional. Those are the only homomorphisms between the vectors, the additive group in the vector space and the additive group in the base field. And so you get exactly the same thing. So the noise here becomes the addition of the Gaussian noise, because the notation is additive. Instead, we'll be using multivariate notation. But these are equivalent if you switch multivariate to additive notation. So we recover LWE as a generalization, but generalizations are not useful if you don't get anything else. And by the way, you also capture ring LWE, modular LWE, and all the other generalizations. They all fit into this framework. The question, though, is can you get something more than that? And in particular, that's where we are trying to find a suitable non-commutative group. And Nelly did a great job at explaining you the platform you're going to use for this setting, which is the Burnside groups. So what you get if you use a Burnside group in this learning homomorphism noise framework, we call them learning Burnside homomorphism, and we could denote it with BN LHN. So the LHN problem is the general problem where you don't specify the framework, so it's more like of an abstract presentation. And instead, the BN LHN is the actual problem that you are studying. So we call that learning Burnside homomorphism noise. And the way you instantiate it is for the first group, you choose the Burnside group with the exponent tree and then generators, and it's going to be your security parameter. And instead, for the base group, you choose another Burnside group of small order, in particularly finite of 4 or 5. That's what we are toying with. if you think about the case of LWE, also there if it's finite, the security parameter doesn't really play a big role in the base field. Yeah, it's FP and sometimes P is polynomial, so maybe it makes sense to look at R logarithmic in N in the security parameter, but it's not necessary to look much beyond. And for now, we're looking at the case of just like constant, which you could do also for LWE. You could imagine working with LWE in the case that the prime is 3, although there you cannot do a distribution being Gaussian, you have to do something like a Bernoulli. So it's become more like an LPM kind of assumption. At this level of abstraction, they are pretty much like equivalent to LPM. The noise distribution is a parameter here. Okay. Then distribution we said over the preimage is uniform. Now, turns out, something we're going to discuss a bit later in a bit more detail, that the group Burnside group with N generators and the one with R generators are compatible in a sense that you can always map, you get a lot of homomorphism from the first to the next, from Bn to Br. I'm going to say a couple of words about that, but turns out that this set is finite, it's exponentially big in N, and so you can take just uniform distribution on that. So hold on that, I'm going to say a couple of more words on that. And next, a bit of like magic in the distribution. How do you go? What do you do instead of the Gaussian distribution? Here we do something completely different than Gaussian. And you can think of that as a random walk in the Cayley graph. So Nelly showed before a picture of a Cayley graph for the example of the Burnside group of exponent 3 and 2 generators, which was the ball where the quality were holding. And again, the Cayley graph is a representation of the group where nodes are the elements of the group and vertices are the group operation. And because you have multiple generators, this is actually a labeled or a colored graph. And in there, you can represent identity as, you can label one node as identity, and then you can look how far, how many elements there are not so far from the identity. So if you start from the identity and you only multiply by a bunch of generators, where do you get? So this expression here, where you take a random permutation of the generators and you give random exponents to them, and then you look at their product, correspond to starting from the identity and then choosing one of the generators, deciding whether to use it or not, whether to use it inverted or not, and then sticking it in your expression, and then moving to the next generator, deciding whether to use it or not, and which in index and so forth. So this is just like a permutation of the generators. Some of them may not occur because the exponent may be 0. Some of them may occur inverted. So it's kind of like a random walk over this Cayley graph. An important property, which is the reason we chose that, is that the exponent here is completely random, so they're going to have a good randomization property when you multiply by the image. So we're going to discuss that in a second. So then the problem becomes that you're given a random A together with a noisy image, where the image is being perturbed by this random walk in the Cayley graph. So, okay, so I'm going to denote this zero distribution with BR, because it's like a ball in this Cayley graph. You're making a ball radius R starting from the identity. So that's as much geometry we're going to be able to recover in this setting. Unfortunately, by looking at it algebraically, you lose a lot of the geometry of the LWE setting. The only bit of geometry you're able to recover is through this notion of Cayley norm. And so that's like you're going to be referring to this BR as the bolts of radius R. And so the assumption we make is that if you're given a pair of a preimage together with a perturbed image by a noise which is in the ball around the identity in the Cayley graph, that's going to be indistinguishable from a random preimage together with a random element in the image. And the assumption is defined for the average case. And what we'll prove is that, in fact, the assumption has a worst case, has a random self-reducibility. So that, in fact, if it is true for the average case, it's also true for the worst case, if the homomorphism that you're using is actually surjective homomorphism, which is going to be with overwhelming probability in our case, because we are going from a big set Bn into a much smaller set Br. In our case, R is constant. And so it's, even if you don't worry about exactly choosing it as a surjection, it's going to be a surjection with overwhelming probability if you take it at random. So that's what we're going to talk in the remaining time, in the last 15 minutes. Now, Daniele did a great job at motivating random self-reducibility for me, so I'm going to say very few words. We think that random self-reducibility gives some sort of circumstantial evidence that the problem is hard, because if you try to break the problem, well, you have an easy time at setting the question. If you can break it for a random session, you can choose your own instance. If you can break for any instance, is bad. And on the other hand, if you want to use it for cryptographic application, you can take a random key, a random homomorphism, and if any homomorphism is strong, a random one is going to be strong. So it's easy to use in the application. It's easy to break if the assumption is false. So we think that it's an important trait for assumption to have, and the fact that this property holds for these groups to us suggests that these actually are a good instantiation of this framework. I'm not going to say much more because, like I said, Daniele motivated the importance of random self-reducible problem. So the next thing, before we can actually prove this random self-reducibility, is to understand a bit more what these secret keys are. Like I said before, in our case, secret keys are homomorphisms between these groups, between a group with a lot of generators of this type, of this family, and a group with much fewer generators of the same family. And so if we want to try to understand how difficult it is to recover a key or to figure out what the key is being used, we better understand how this key works. What are these homomorphisms? So an important thing, the last bit of background that you may need to know to understand these keys is the notion of relatively free. This group Burnside groups are also called free Burnside groups because they have the property that if you take any other group which has the exponent tree condition, where every element has exponent tree, every element per tree is a given identity, then you can always define a homomorphism from the Burnside group into this group P. Notice that in general, it's not true that given any two groups, you can define homomorphisms. If you have ZP and ZQ for P and Q, which are co-prime, then there is no homomorphism from ZP to ZQ other than the trivial homomorphism. Why? Because element in ZP have a certain order. If it's the additive group, it's P. If it's the multiplicity group, it's phi of P. And the one in ZQ have a different order. And so unless you do the trivial homomorphism map everything to one, there's going to be a conflict. They're going to be laws that are true in the first group that are not true in the second group. Now, in the case of Burnside group, the only law that's there is the exponent tree. So if you have another group of exponent tree, for example, F3 or F3n, like vector space over F3, those have the property that every element multiplied by 3 gives you the identity, gives you 0, the additive notation. Then you can always have homomorphisms from any Burnside group Bn into F3 and F3 of n and so forth. So that's said, this fact it's called freeness in the category of group of exponent tree. So without going into more of the details, this says essentially that it's easy to define homomorphisms from Bn to Br, because of course Br also has exponent tree, just fewer generators. And the way that you do define homomorphisms is just you choose a mapping for the generators of the first group. So you decide where to map the generators, and then there exists always a unique homomorphism that extends linearly, homomorphically, to the rest of the group. And in particular, this means that in our case, we're choosing the group P to be Br for R think of R as a constant. Then you get that for each of the n generators in Bn, you have a choice of 3 power R, R choose 2, R choose 3 possible images, and for each of that you get different homomorphisms. So the number of homomorphisms, which in our case are the secret keys, is this kind of exponential. So even for R a constant is exponential in n. So our key space is big, even if you choose R to be something like 4. Okay? So that's the first thing we need to know about homomorphism. The next thing that you need to know about homomorphism is that even though we are looking into non-commutative group to try to find additional hardness, to study them, you often try to go back to the Abelian case. So you do what's called an Abelianization. You try to look at them from a point of view of Abelian groups. And Abelianization in this context comes in 3 shapes. You take a group, you can try to Abelianize the group. You can try to Abelianize the elements of the group, and you can try to Abelianize an homomorphism between groups. So let me start from Abelianization of a group. The Abelianization of a group is just a way to say, well, Nelly was describing these commutators, which were what you needed to recover Abelianity. So if you have in our group W1 and W2, that's not equal to W2, W1, but it's equal to W2, W1 with the commutator W1, W2. So you don't get equality, you don't get Abelianity because you have this additional factor. So what you can say is, what if I look at this as a subgroup, the subgroup which consists of all commutator of weight 2, and I take the mod, and then I mod it out so that this equation holds modulo the commutator of weight 2, then I recover Abelianity. Okay, so that's called Abelianization. So Abelianization. Yes, I mean that. Yeah, sorry. That's a good point. This is incorrect because you need the normal closure, so you need to conjugate by element of the group. Thank you. So here there is a mistake. Here is actually, this is not suffice. You have to add conjugation by element in the group. So anyway, once you do that, if you mod out from the group the commutators of weight 2, and in particular the commutators of weight 2 of weight 3 are special type of commutator of weight 2 when the second element is not a generator, then you go back to an abelian case. Okay, so that's called the Abelianization of the Burnside group Bn, and what you recover there is the vector space F3n. Okay, so then, besides the notion of the Abelianization of the group, you can look at the Abelianized individual element, which means how do you map an element from the Burnside group to an element in its Abelianization. And that pretty much consists of taking the prefix in the exponent list. So in other words, the element in the Burnside group have this long exponent list, first exponents for all the generators, then the exponents for all the commutators of weight 2, and then exponent for all commutators of weight 3. When you look at the Abelianization, essentially we're saying, modulo changes to the Burnside elements of weight 2 and 3, then the high-level information, the first-order information is captured in the first list. So the Abelianization discards the rest of the information and just keep the remaining part. And so that we call the Abelianization map rho of n. And of course, that's defined for every Bn and Br. So we're going to use rho of n for the Abelianization that is for n generators. There is another one for R generators. We're going to call rho of R. And the last concept is the Abelianization of the homomorphism. So if you have an homomorphism that goes from Bn to Br, so it's an homomorphism in non-commutative group, then you can look at the homomorphism between the corresponding Abelianization, which in other words, one way to think of it is here you're taking an element which has a structure, you go into an element which has a similar structure for fewer exponents because you have fewer generators. So what you can do is just look at the prefix of generators here, and look at the prefix of generators here. You're going to get a map between the corresponding vector spaces. And this map is compatible in the sense that if you first Abelianize and then map, or you first map and then Abelianize, you get to the same place. So this diagram commute. Now that's not a trivial fact. It follows from the fact that Abelianization are universal for homomorphism into abelian groups for Burnside. And that's category theory, which happened to work nicely in the case of Burnside group, but it's not for granted that this thing would commute. So we're going to be denoting the Abelianization homomorphism phi with phi bar. So we're going to use the phi bar notation. If we bar something, means it's a Abelianization of the corresponding homomorphism. All right, so let's see if we can try to understand this Abelianization by using them for a second. And in particular, one question would be, are we getting anything new here? Do we, like a valid concern would be, is it the case that we need the LWE problem in the abelian case for modulo 3, do we need that to be hard for our problem to be hard? In other words, what happens if you give me the samples A and B, which are in this which lives in this non-commutative group, A is in Bn and B is in Br? What happens if I try to Abelianize them and try to break the corresponding problem for the abelian case? Am I going to be able to tell whether you are using homomorphism, it's random you're doing that? So, in other words, if I look at the assumption I'm making, it is that pairs of the form pre-image in Bn and then image in Br with noise are distinguishable from pairs in Bn and Br. What happens if I Abelianize them? Abelianizing them means I apply the Abelianization to both elements here and to both elements here. This is the easy part. Of course, if I Abelianize a random element, they're going to get a random element, because that's just a list of first exponents. Random element here means all the exponents are random, so in particular the exponents in the generators are random. And the same for here. So this maps onto the uniform distribution. Now, what happens if I Abelianize an element here? Well, A was also random in Bn, so rho of A, the Abelianization of A, is going to be uniform. How about this side? Here, by the diagram before, I'm going to get the same thing if I Abelianize the pieces and then I apply the operation after I go there, which is going to become sum, because now I'm in F3n, F3r. So in this case, it's going to be the image of phi of A, whatever it is, plus the image of the noise. Well, that's where the reason for choosing the noise the way we chose was. If you remember, the choice was a random list of exponents permuted somehow. Now, if you Abelianize the element, all you get is only the exponent of the generators, which we chose at random from FR, which means that the Abelianization of this noise is random, and so this is going to be by one-time path, it's going to be random. So the distribution you get here is actually random because you Abelianize this into a random vector, and random because the noise is going to become like a random one-time path. So in this case, if you Abelianize the sample, you get the same distribution that if you Abelianize the reference distribution. So there's no way to distinguish distribution once you Abelianize them. If there's any hope of distinguishing them is before you Abelianize them. After, they become the same distribution, which means that it does not suffice to break LWE. Even if you can break LWE over F3, maybe this assumption over B3 is still going to be hard. That doesn't mean that there is no reduction. It means that this approach fails. So I cannot prove to you that they're independent as assumption, but I can tell you that obvious approach, like working with Abelianization, which are pretty much the only thing that are known about these things, don't work. Because if you do them, then what you get is things that actually cannot no longer be distinguishable. Okay, so that suggests that this is just also like to give a feeling of how you work with Abelianization. Now, don't have a lot of time, so maybe I'm going to stick with the intuition of how do we prove the random self-reducibility of the assumption. It's going to be in 2 steps. The first step is generic, actually works for all assumptions of this type. And interestingly, it's not really used much in the case of LWE because you have so many other properties in the case of vector spaces. That's true in any setting, however you instantiate it. And the second step is that is only true for the case of Bn. I mean, we know only how to prove it in the case of Bn. And that's going to say that actually this randomization trick, it's complete. It's completely randomized the class of keys if you stick with the surjective Siegel keys. So, okay, so what's the first part with the first trick? The first trick, we can call it domain reshuffling. And what it says is that if you take a random permutation of the first group, and before disclosing the pre-image, you permute it according to this random permutation, then what you get is going to be also a sample from a distribution, from an LWE-like distribution for a different Siegel vector. And here the reason that we have to choose the inverse here is because in general, we like to work with this operation. In general, it's not easy to invert an automorphism non-commutatively. So even though it's an automorphism, even though it's a permutation of the groups, it's not easy to invert it in general. So that's why we work it like this. Okay, so the statement says that if you have a sample of the form random A and B, which is phi of A times E, and you pre-process the first part with alpha inverse, then what you get is a sample without changing B at all. Is also a sample according to a different noise distribution. And that's just simple algebraic modification. So, okay, what you're saying is that this thing A prime B should look like A prime with a noisy image of C composite with the alpha on A prime times some noise that comes from probability distribution. And well, if you plug things in, B is phi of A. You can think of phi of A as phi alpha alpha inverse. Alpha inverse of A we call A prime. And so you get A prime phi composite with alpha of A prime in E. So here you don't need to do anything with the B side, because on the B side, if you apply an homomorphism, we don't know what happened, because there is a noise which doesn't commute. So we may actually not get what we wanted. So this does not completely randomize the secret, but it said that if it's, you can always translate your secret by a permutation that you know. Now, if this permutation is also an homomorphism, so it's actually an automorphism, then for the case of Burnside group, we can prove that this actually is complete. Meaning that for any 2 surjective maps from Bn to Br, there is always exactly one, it's actually unique, automorphism inside Bn that moves the first into the second, such that you can look at the new homomorphism as a composition. So the previous trick was saying that if you have an instance under phi, you can always randomize at an instance under phi compose alpha, but it doesn't guarantee that the instance of the form phi compose alpha covers the entire space. Instead, this said it does cover the entire space, because for every phi prime, there's always an alpha that moves phi into phi prime. And the intuition of that, which is the statement which is written here, the intuition of that is in the following picture. Here, the first homomorphism goes from Bn to Br. Unfortunately, I'm calling phi star here. I should have called it phi prime in the previous notation. In G notation, it's called phi star. And I would like to split this homomorphism from Bn into Br into 2 steps. First, an automorphism, so a permutation, a bijection from Bn into itself, and then an homomorphism from Bn into Br. Now, it's obvious that you can always find a map here that goes from Bn into Bn, such that phi star is equal to first applying the beta and then the phi. However, notice that here we're going from a big set to a small set. So nothing prevents the 2 steps from happening like you go from a big set into some subset here, and then from this subset into the small steps here, because you have a lot of space to lose from here to here. BR is much smaller. And so it could be that actually you are losing something here, and then you're losing the rest here. If that's the case, then this is not an automorphism, which means that if that was all we got, it wouldn't be clear the distribution is uniform, because perhaps you get some surjections more often than others. So what you need is now a way to patch the arbitrary homomorphism that you're given by just an Abelianity, just a commutativity argument, into a full automorphism. So maybe like I'm going to take over like by a couple of minutes without going too much into the details, but the technical lemma that allows us to prove the theorem is that even though by going to Abelianization you lose a lot of information, turns out that a map from Bn into Br is surjective, so it covers the entire codomain, if and only if the corresponding Abelianization is surjective. Now, one direction is obvious. If this is surjective, then this must be surjective. But what's not clear is that if this is surjective, suffices for the entire thing to be surjective. So one side is just a so-called diagram chase, because you must have Abelianity in one direction, and because we proved already this thing commutes, then you must be surjective in the other direction. The other side instead requires a couple of additional tools, and in particular requires the fact that Nelly was pointing out before, this commutator weight for R1. The terminology here is that the group is actually nilpotent. If you start taking factor group out of the group, it terminates soon. That suggests that you can always, once you get a list of generators modulo a subgroup, then you can always bring it back to a full list of generators. And the list of generators in here, in the Abelianization, is just a list of generator modulo a specific subgroup, the commutator subgroup, Bn. So that's why you can also generalize it in there. Okay, so that's essentially the lemma I said before, rewritten in the specific case of the Burnside groups, which is that if you have a list of, this is an overdefined list. You have m elements in Br. Those m elements actually generate all of Br, if and only if the corresponding Abelianization generates all of F3R. And this is something you can test by rank arguments, and so you can actually, and this is not only if and only if, but you can also recover the corresponding basis. All right, so now, very briefly, so this is trying to suggest that this is viable from the point of view of hardness, that you get some hard problem. We don't really know too much about this problem other than they are random self-reducible, which suggests that, if you want to try to break them, you should have an easy time breaking them. So if people can break them, of course, it could mean that they don't care, but hopefully people at some point are going to start to care, and then if they cannot break them, that's because the problem is hard. The other side, though, is actually using them for applications. Now, it's clear that the assumption already gives you some sort of pseudo-randomness. So building pseudo-random generators is pretty simple matter from that, and so what you get as a corresponding encryption scheme is something similar to, in a sense, you can think of that as something similar to Rabin encryption, where you have two different types, the residues modulo the squares and the non-residues, and you encrypt at 0 with the residues and the 1 with the non-residues. Here, what you do, you need to look a bit more again into the geometry of the group, which has to do with the Cayley norm. Turns out that this group have a pretty big diameter, so there always exist elements which requires a lot of generators and inverses to write. And for this reason, you can always have a way to tell whether you have added, you sneaked inside an element a copy of a large element or not. So one way to get bit encryption is to fix one such element which exists by counting argument, and then in the case of small group, you can do an exhaustive search to find them. So you fix an element which has a large so-called Cayley norm, meaning that the only way to express it as a product of generators and inverses, it takes a long sequence. And then to encrypt at 0, you just give a sample from the distribution A and B, and so here I'm missing a power T. So to encrypt at 0 should have been just A and B, and to encrypt at 1, then you send A together with the tau multiplied by B. Now, because the norm of B is always going to be small, then when you look at the distance between phi of A and B prime, when you apply the homomorphism, somebody who knows the secret homomorphism then can compare whether these two elements are nearby or not. And if they are nearby, then if the distance is small, then you assume that the whole perturbation was due to the noise. If they're not nearby, then you assume the perturbation was due to the presence of the big tau.
So yes. Have you computed
this norm? Because it doesn't follow from the
Correct.
normal.
And that's the reason why R is a constant. We don't know that it's not easy to compute, but we don't know how to compute it. So right now we pre-compute the entire norm. And that's also how we know the sizes. There are bounds on the sizes, but the bound that you get just by the bounds that you can prove are not great. When you actually do the computation, then you see that these elements are actually pretty big. So you could be able to sneak maybe more than a bit, maybe like 5 bits. But that's, those are constants. Yeah, it's a good point. The computation of Cayley norms is not, in general, is not known to be polynomial time. It could be for these kind of groups, but nobody has looked at them. So we don't know if these are easy to compute or not. We don't need them in this case because we're working with a constant R.
So how's the message encoded?
The message, here I have a typo. There's a missing T here. If the message is 0, you don't include the tau. If the message is 1, which is like the way to bit encrypt with LWE when you add Q over 2 or you don't add Q over 2. So that's pretty much true for all the type of LHN assumptions. Now in this case, you also have an hardness for the corresponding assumption. And the reason why this would be semantically secure is because if the assumption is true, then A, B looks like a random pair. But if this were a random pair, then this would be random. And so there is no difference. This is one-time pad. So it's like computation one-time pad. So that's how you decrypt. Now already going beyond going beyond mini-crypt and try to get public key cryptography, you start to get a challenge. You could try to do the same trick as LWE, which is you include a bunch of encryptions of 0 in the public key, and then the encryptor with the public key take a random subset. However, here non-commutativity bites you, because if you do as a random subset, now the order matters. Things are no longer going to commute. You don't know that adding lots of small noises is going to be a small noise. It is a small noise if they're all one after the other. But if they are intertwined with the regular items, you don't know. And even for the case of Burnside group, it doesn't work out. Now, there are tricks you can try to play with a noise distribution. Try to use a noise distribution that commutes, so that actually it's going to work out. But that's going to cause the problem of, you remember when I was showing the connection with LWE, that there is no connection by abelianity? If you use another type of error, which has abelianity here, then you require LWE. So it doesn't make sense to use an error distribution which is abelian. Otherwise, you essentially may as well just work with LWE. So already going beyond and getting something like public key encryption is tricky. It requires some sort of generalization of the leftover hash lemma, where instead of doing inner products, you look at these automorphisms. And we think something like that may be there, but we don't have a specific result. So at this point, that concludes pretty much this exploration. So what we've done is to, first of all, look at LWE from an algebraic point of view, and you don't get as much as looking for it as a geometric point of view, but you still get something different. And then we coupled that with the exploration of these Burnside groups, which are a different type of mathematics, which is not used a lot in our community. They have a lot of structure, and they may also be useful for other coding applications, but we've tried something like that with not much luck. It looks like you should also have information theoretical use of them. And then we studied the hardness of one of these assumptions, and in particular, we were able to prove that they're random self-reducible. One thing we're working on, and it doesn't seem to be working easily, is a decision to search, which is the case for LWE, but there you seem to require the fact that you're working over a field. So here we lose like half of the structure, and those arguments don't go through as well. So with that, I'm going to let you go and catch your luggage or go to San Francisco. But if you want, you feel free to ask us questions before you head off.
So to what extent are we confident that the problem is indeed hard? And would you go to the extent of removing the noise to encourage people to cryptanalyze it? Maybe, without the noise, might be an easier target.
The thing is, without the noise, we lose the random self-reducibility. So without the noise, I wouldn't be confident. With the noise, I would be confident to even suggest small parameters like 50 generators. Because it's not clear, the security parameter is number of generators, but the size of the group is cubic. It's exponential in the cube of that. And unless there are nice things you can do, then that should be enough. If not, then you may need to have something like 100 generators. Yeah.
What do you mean that without noise?
noise, you don't have random self-reducibility. Is it like that the problem becomes easy for automorphisms? Or?
So what I mean is that it's going to require LWE. Let's see. Yeah, I mean, I don't know that you don't have it. I cannot prove it. I don't know that you don't have it. I cannot prove random self-reducibility if there is no.
But I don't know if they have. Shouldn't it also work when? Shouldn't your proof also work when there's no error? How's the error essential for the random self-reducibility?
No, yeah, you're right. Actually, maybe not for the proof. There was something.
So the only thing I could think of would be that I don't know. You needed endomorphisms for your random self-reduction, and maybe the problem becomes easier for
if it's not noisy.
Yeah.
Yeah, we haven't really, somehow like we felt like having the noise there was as an edge, was like as an additional safety. We haven't looked too much at the case, but I think it would be already interesting to break it without noise, so that we know that LWE is trivial without noise. So it would be interesting to know what's the best you can do without noise there already. I wouldn't expect it to be easy, but I wouldn't necessarily expect that you can get hardness results. So that's why we're not looking at that. But from the cryptography point of view, actually, it would be a great first step.
Yeah. So if there are no more questions, let's thank Antonio.